Good afternoon. This is Dr. Ray, and I will discuss assembly language memory examination with EB this afternoon. This is, I think, the third time that I've tried to start this session. Now I'm using Google Chrome. Maybe it will behave better. Firefox won't let me switch back and forth with multiple screen shares, which it used to do. So I will switch to the EB window first. All right. Let me back this up and let's wipe out the code. All right. Now we have hello.asm, no code, and we should be finished running it. And I'll start it like I did earlier. Using the file menu, there's a template section, and I want to have an assembly program. The easiest way to do it without knowing any assembly is to use the template program. All right, now this program, if I switch to the terminal window down below, and I click on the green alien icon, it runs the program and it prints hello world. That's a miracle. Now, generally, we would prefer to set a breakpoint, which you do by clicking on a line number. I clicked on the 9, and now when I click on the green alien icon or the run button, you can see that it has highlighted push RBP. It has not executed that statement yet. I'm going to switch back to the assembly data window down below, and we can see that we have assembly data. Now, we have up here segment.data, and within that we have the array MSG. LEN is just a label that is equated to the length of this. Dollar is the current point of assembly. Dollar minus MSG says take the current point, subtract from that the beginning of MSG, and that will be just the length of MSG. After that segment, we've started entering things in segment.text, which is for instructions. Now I'd like to switch to another window and look at the listing file. And let's see, hello LST. All right, Chrome, Hangout, screen share. I'm back. Yes, today I'm okay with Chrome, but not with Firefox. I will remember. All right, the listing file shows some lines before the code that I want to see that come from eb.inc for include. And here we can see at line 368 is the first line that is from the source for hello.asm. And here we see the message hello world, and here the .text, and I'll go through these things a little more carefully. We have line numbers of the file over here. The next column is the address. You'll notice these say 0 and this says 0. The first is relative addresses in the data segment, and the second sequence is relative addresses in the text segment. These two lines are together, and this 6C is not also at 0. The 0 is listed twice. I'm not sure why. But in any case, we have MSG is the label for it. DB means data bytes, and then either single quotes or double quotes work. Capital H is a 48 in hexadecimal. A lowercase e is a 65. L is 6C, so there's 6C twice. This change in color from purple to green is kind of ridiculous. things look pretty good until you hit this part. The assembler doesn't provide a way of using \n like one could use in C or C++. You have to use either an explicit 10 in decimal or A in hexadecimal. And you can see it's a 0A over here. In the text segment, the relative address for the start of main is 00. The first instruction, push RBP, is hexadecimal 55, 1 byte. The next instruction takes 3 bytes. The next one takes 5, but this part, the 0D and the rest of it, is the number 13, which is the value of len. That's the length of hello world and a /0x0a. Interestingly, there is no terminal 0 at the end of this sequence of bytes. Putting things in quotes is not the same as it is in C or C++. There's no terminating 0. If you want a terminating 0, put (0). Then move, let's see, the next instruction is LEA, RSI, and then MSG. The part that's in the brackets corresponds to the MSG that's in the bracket. This is going to be replaced by the address, which is 32 bits for items in the data segment. Your program can have data that is using addresses higher than 2 to the 32, but they're not in the data segment. These are pieces of data that you might allocate, and data that's on the stack has higher addresses. All right, so this instruction requires 8 bytes. One before it was 5. The first part of this instruction basically means load effective address RSI, and then these 4 bytes are the address. And here we've got a move, and again we've got BF as the instruction, and the 1 is stored as a 32-bit number. Then there's a call to write, which is 5 bytes, and this F6 FFFFFF, however many Fs that was, that's not the actual address. That's going to also be replaced. And you'll notice that the call to exit has the same number in here. So they're not the same address. All right, so we've got some instructions that are 1 byte, some 2 bytes, some 3 bytes. I guess there are some that are 4, 5, I suppose 6, 7, 8, maybe a few more bytes. I don't know what the maximum is. All right, now I want to get back to the source code. Temporarily, I'm on air. All right, now in this source code, we can put multiple pieces of data in here. And if you put it on a line, the label on a line with the instruction, you can skip the colon. Whether it's a good idea or not is hard to say. And if you want a terminated string, you would do that. All right, now we have 2 labels. Let's run the program again. And we have the variable MSG, which is at address 602.098. And as you can see, it's 6 hexadecimal nibbles. And this one is also. So that easily fits into a 32-bit number. And you can see that the address is 098. And addresses for pages of memory start with 3 hexadecimal nibbles. They're all equal to 0. So there are 98 hexadecimal bytes before MSG that are technically part of the data segment. That is something that's not part of my program. It may be something provided by the C library for the function that calls main. I don't know exactly what's there, but there's something. Adding one line, segment.data. All right. Now, looking at some of the pieces we've got, we have two segments, and we can also put in a segment.bss, and I'm not going to cover too many pieces of data, but let's put in segment.bss. That has a crazy name. It means something like bulks or block started by symbol, and who cares exactly where that came from. Let's give it a label X, and here things are different. With data, we give it specific data that we want to store. With BSS, we give it a number of bytes. So let's run this program as is. Now we have X, and as you can see, it has 10 bytes that are all 0. So it's initialized with 0, but we didn't tell it the value to use. All right, this icon to the right of the green alien is the next instruction icon, or next, and the one to the right of that is step. I don't really want to step into the right code, but I could. All right. But we see these pieces down here, and there's a little bit we can do with this. We right-click, we can change the format. We can tell it decimal 1 byte, and the capital H is actually 72 in decimal. We can tell it decimal 2 bytes, which puts the H and the E together to make that decimal number. It's not meaningful, but we can do it. You can do hexadecimal 4 bytes or 8 bytes. Here we have hexadecimal 8 bytes, and the array had 13 bytes in it. So it's showing us 1 8-byte quantity and not 2, because there aren't 2 of them. All right, we can choose char format, which is more appropriate. It shows it as characters. And here we can see hello again for the message to, and the new line character. And in the presentation by EB, it shows it as \n, which, as we've discussed, you can't do that in the code up above. And you'll notice when you're in the char format, if whatever you're trying to show is not something you can represent with \n or \t, then it shows it as a hexadecimal byte. That 0 byte, which is a terminal byte, is done like that. All right, X. Oh, we can show it as binary format. With 1 byte at a time, binary format is pretty boring. Let's try binary format for hello world. All right, so the H is this binary pattern, and a lowercase letter has this bit. This is 0, 1, 2, 3, 4, 5, 6, 7. So bit 5 of a lowercase letter has a 1 turned on. And bit 6 means 64. So these numbers for uppercase letters begin with 65 for an A, and the lowercase letters, it's a 64 and a 32, those begin with 97 for an A, and whatever that is, let's try it. Decimal 1 byte, 101 for an E. All right. There's not a lot more thrill to be gained from that. Now I'm going to put some other pieces of data in here. All right. Instead of data bytes, I'm going to put data words. 1, 2, I can put as many of them as I want. And a word in this terminology is a 2-byte integer. So I'll give it a 2-byte integer that I can recognize. How about 10FF? That's 2 bytes. Now we see nums, and unfortunately, I haven't put any effort into digesting the source code for the assembly code. I'm simply examining the object file and the executable file using a tool called nm, which I assume stands for name or something like that. And with nm, I can find the location, the address of variables that are in the program. I can determine whether they're in the data segment or in the BSS segment. And I can find the next address after that thing in memory. And by subtracting, I get at some size that is at least as large as that I've specified. I think it's matching pretty well right now, but I'm not really certain. These that are back to back, there's no gap between them. If I wanted to, I could make a gap appear, all right? You'll notice that nums begins with a B3. Probably we would prefer before 2-byte integers. Maybe we'd like to tell it a line 2. The layout of your code is pretty arbitrary. Until things get complicated, I tend to put all the instructions in the same column and all the operands starting in the same column, but it doesn't really matter much. All right, with that align to statement added, now it has B4 as the address for the beginning part of nums. And you'll notice that these numbers, we've got 0, 1, 0, 0. That's the first number. That's the 1. 0, 2, 0, 0 is the next one. 3, 5, 6, and then FF1, 0. And if I show that in hexadecimal 2 bytes at a time, then we see it as 10FF. It may be important for you to be aware that the numbers are backwards, but maybe it's not too big a deal. In addition to words, you can have double words. And it doesn't matter how many you put in here, but double words are 4 bytes in size. So I'll put in something with an explicit 4-byte pattern. How about 0, 1, 0, 2, 0, 3, 0, 4? All right. So now this ints has these things spread out a little bit. You can see that the 1 is in the first 4 bytes, the 2 is in the next 4 bytes, and then the 1, 2, 3, 4 pattern is in this next 4. So this one should be properly displayed as hexadecimal 4 bytes. All right. And there is no reason why you have to stick with 4-byte integers. How about the number 2.75? Well, that's 2 divided by 75. How about Well, who cares? 2.75, 2.85. Let's stick with 75 for the moment. All right. So now we have the value for 2.75 in here. But we can't see it because it is a float value, and we can display it as floats. You can see that here we have 2.75, and unfortunately I've got in this thing called ints, I've got some integers and I've got one float. We can examine that float in more detail as like a binary floating point number. And as a binary floating point number, that number, the last one, is 1.011 base 2 times 2 to the first power. So 1 times 2 to the first power is a 2, and this number here is 3/4, I guess. Is that what it is? 1.0. This doesn't seem right. I think maybe I've got a little glitch in my code. That should be 1.11. Something for me to remember to look into. 2.5 would be 1.1 times 2 to the first. So let's hide this garbage. All right. Float format. See if we got the float fields correct. I'm not too sure about that either. It's the same basic problem. All right. Moving on. The next size larger is quads. And doubles for double words. And then we have quad words. So DQ. Now quad word is 8 bytes. So I'm going to put a couple of smaller values in here, and then I'm going to put in a monster. And I know the 0 doesn't really go after 9, but that gives me 16 hexadecimal nibbles. It should be correct. Let's see. Yeah. And things look a little goofy. Things are backwards. We got the 1, then the 2, and then the other number. And the last thing we can do with DQ is to define a double value. So if we use a number that is DQ for quad words, and we use like 1.85, well, 86 will work. Then we have Z2 in here. You can see we get a lot of bits turned on. It's 8 bytes. And if we tell it to put it in double format and display it as a double, we get 1.86. I don't know if I've got this thing working right as a binary floating point number or not. It was 1.86. This one right here should be a 0.5, and this should be 2.75 might have been correct. Well, it doesn't matter. I'll worry about that some other day. All right. You'll notice this pattern. It keeps on showing up some bits out here. The problem is we can't really represent 1.86 completely accurately as a sequence of binary numbers. What you can actually store in one of these floating point values is some number with 1 point, some sequence of 1s and 0s base 2 times 2 to a power. That's all you can store. And that means that you can, after the fraction, you could be adding things like 1/2, 1/4, 1/8, 1/16. And there's no combination of those that works out exactly for most numbers, like 0.1 doesn't work. Let's put 1.1. Shorter sequence or shorter number will give us a quicker repeating sequence, I think. Z2. Now with 1.1, we get 1.000110011, and it doesn't take much imagination to have some suspicion, which could be verified, though we're not going to do it, that this is a repeating binary fraction with 0011, which would repeat forever. It doesn't stop. If you were to divide it, you could keep on dividing forever, but you have to stop with 8 bytes worth of value. All right, so we've looked at integers, floating point values, characters. Let's see what else there is under this menu system. Decimal and hexadecimal, various sizes, binary formats, and we're not going to do this real soon. You can, if you've got an address, you can define a variable with the address. That would be useful if you were going to allocate some memory, and then you could have the allocated memory stored in a variable. And at that point, you may need to look at that memory that you've allocated, so you define your own variable, which would show up in here with a different label, one you create on the fly. All right. You can define variables from the code itself. All right. Let's see. Let's change the code just slightly. I don't really like using write and exit, so I'm going to change this and quit using exit and use printf. So with printf, you only need the one parameter if you're just going to print a message. And my value, message 2, had a 0 byte after it. And I'm going to get rid of these comments. Okay. So we'll need the effective address of MSG2 in register RDI. And there's one little glitch. You have to store in register EAX or RAX a 0. This instruction doesn't matter anymore. There's only one parameter for printf. And instead of doing this kind of stuff, let's do XOR EAX, which is another way of zeroing it. And we'll do the standard kind of thing, leave, and then RET stands for return. This looks a little more rational. Going to switch to the terminal window of the program to clear the output, and let's see if this works. Not too well. Undefined symbol return, where is return? Line 26. Oh, I got call return. I don't know what I did, but I can't type very accurately. All right, so we get some registers collected, and when we call printf, after it executes that, you see hello again. And then leave will change some registers around, and return returns, and then you're out of the program. It's technically, it might still be executing, but no big deal. let's see, there's another window called the data window, which is for higher level language code. And let's see. Let's see what happens if we step into printf. Yeehaw. We are now in the printf at PLT function, and it doesn't tell us about any registers, anything. Let's tell it to continue on. And let's step on through the program. Aha. Here, using this high-level language data, when you get past main, you see that we're in the function labs underscore labc underscore start underscore main. And the parameters are quite a few weird things. If you really wanted to, you could find out how this actually works. And this is the most recent function on the runtime stack. And this one down below is the one that started with. Underscore start is the first function that is actually executed in a program. And we can see that there are two functions that are not generally seen to us, but that are used in Linux when you start running a program in main. All right, I haven't been watching the chat, and fortunately there's nothing there for me to respond to. All right. I think this is probably good enough for today. I got off to a rocky start. Next time, I will know to use Chrome to start with. Apparently, Firefox doesn't work very well with Google Plus Hangouts, at least this version. Till next week, bye-bye.